Hello and a very good morning to all of you. Today in the lecture, we will be discussing about their fifth experiment, that is FTIR spectroscopy or Fourier transform infrared spectroscopy. First of all, what is the meaning of spectroscopy? It indicates the interaction between matter and electromagnetic spectrum. So let us understand that if this is a matter, let's say we have a substance and a light is being, so definitely a spectra will generate, right? This is termed as spectroscopy as we discussed in the previous classes. Now, what is FTIR? We know that every substance has a particular chemical composition. Now, it's very important in material science, in biological science, and different other sciences to understand what is the chemical configuration that is persisting in a sample, due to which the properties are there in the sample. Identify this chemical composition, we use FTIR or Fourier transform infrared spectroscopy. Now, what is the basic principle is that this IR light or the infrared light, first of all, it passes through a sample and then we actually record or we analyze the absorption spectrum. So, let's say, what is the absorption? If this is your sample and if light passes through it, then how much light is absorbed? What are the chemical constituents that absorb the spectrum? That is the most important that we analyze. So, in other words, an infrared spectrum it extremely is important because it indicates the fingerprint of the particular sample. And whatever absorption peaks that we are getting from the infrared spectrum deals with, it's very important, it deals with the frequency of vibrations. This is most important. Okay. It deals with the frequency of vibration. Okay. And most importantly, we try to determine what is the bonding information? Now we know that the meaning of ionic bond and covalent bonds, right? Covalent bond means it's a bond between two atoms by the process of sharing of electrons. So in order to determine the functional groups that are present in the particular sample, and in order to understand the covalent bonding, we go for FTIR spectroscopy. This is particular a picture that shows that how the matter and infrared interacts. If you see very carefully, we know that we know that E is equal to h nu, right? Is equal to hc by lambda. So the simple funda is that if your wavelength increases, your energy will decrease, right? You see, the wavelength is increasing, your automatically your energy will also decrease. So infraspectroscopy deals with the vibrational motions. So remember this, whenever we are going for UV, then it's ionization and electron transition, right? So ionization means this vacuum UV and the X-rays. But for UV visible, we go for electron transitions. Whenever we are going for the infrared spectroscopy, we always deal with the molecular vibrations, how the molecules vibrate within each other. Okay? Now, we will deal with some of the vibrations that are actually happening in the molecules. Suppose this is called the equilibrium bonding. Equilibrium bonding means when the two atoms have no force acted against each other and they are in an equilibrium state. Whenever suppose there's a spring, let's say it's a spring with two ends. If you stretch the spring, automatically the length will increase, right? The bond length will increase. Or if you try to compress it, then the bond level decrease, right? In this way, the molecules vibrate when the IR radiation or infrared radiation falls on the particular objects. So we can find out that this is called stretching. Stretching means, you see, there are two types. One is called symmetrical and asymmetrical. What is the meaning? So let's say this is an atom. This is another atom connected to two or more atoms. Okay. If they two vibrate, like this is vibrating, it's vibrating. That is basically they are. This is called then. Sorry, this is called scissoring. This is called scissoring. Scissoring means whenever like a scissor, it's moving. And stretching means suppose you are having two hands, you are moving the two hands up and down in the same direction. It is called symmetrical. If opposite is asymmetrical. And we also have in the bending part, we have in plane, it is within the plane, and out of plane, that is out of the plane that we have. So this is some of the molecular vibrations in the covalent bonds, as you can see from here, as we discussed. And then we have the instrumentation. So this is an FTIR spectroscope. So this is basically called the sample holder or sample probe. This is the sample probe. Now, why is it so important? Because this is called a sample probe. What it does, let's say you have a sample here. Okay, you kept a sample here. This is your ATR FTIR spectrum. This is your ATR FTIR crystal. Okay. Crystal, we know, and this is basically called the zinc selenide crystal. We have the ZnSe crystal, zinc selenide. So it's very important, right? So we have this part. Sorry, let me just erase it. So the thing is that you have to be very careful about here. There's a particular part called interferometer, and we use a function called fast Fourier transformation or FFT that helps us to convert the spectra into a better way. Okay? It's an easy way to interpret. Now we have the working principle. So this is the attenuated total reflection on ATR. Now what happens in ATR is that the reflectance gets reduced. Okay, and due to the reflectance of the reduction of the reflectance, what happens is that there is a important point. It tries to counter the stray radiation that is appearing from the machine. So it's very important for this. So stray radiation or any other part is basically done by this ATR and Michelson interferometer. So this Michelson interferometer, it does is there is a mirror. There are two mirrors actually, and this is a beam splitter. So what it does, it only focuses the radiation onto the object that is required, and then we get this particular spectrum. Very important part, where this is a graph. This is your percent transmittance or transmittance index, and this is your wave number. So here we deal with the wave number actually, and then like this basically a spectra index. Okay, and this is the different regions of the IR spectra. We have two types of region. One is called the function group region, and another is called the fingerprint region. Right now, there are two main regions actually. Remember this. Whenever between 4000 and 1500, we have the function group region, and between 1500 to 244 for like the rest part, basically it's called fingerprint means it's a unique for each sample for each technique. Remember that spectra is basically unique for each and everything. Okay, then we basically go for the typical IR spectra. If you see very carefully, remember this, the more the absorbance, remember this is very important, the more the absorbance, the higher will be the peak intensity, and the lesser will be your transmittance percentage. And remember this, these peaks actually they correspond to the different atomic vibrations. Like for example, CO stretching, then we have CH bending. Okay, like this basically we have lots of things. You have to correspond the whatever peaks are there. This is basically a broad peak. This is a broad peak. I'm writing this BR, broad peak. This is a sharp peak. This is a sharp peak. SH I'm writing. Okay. This is very important. Why? Because you have to interpret correctly. And this is your broad peak, sharp peak, and multiple peaks. Where we have the multiple peaks are present. Okay. This is your broad peak and sharp peak, or narrow peak you can say. And this is the database or table from where we have to correspond the frequencies. Okay. And there are lots of applications, like we can identify the compounds, we can analyze the functional groups, we can identify the conformations of cyclic compounds, and also we can go for the geometrical isomerism. Okay. And today we will basically first analyze the FTIR samples, and then we'll go for the peak identification, and also we will learn how to do the Spearman prediction of FTIR. A very good afternoon to everybody. Today in this lecture we will try to understand how an FTIR spectroscope works, and as we know that FTIR stands for Fourier transform infrared spectroscopy. So as you can see from here, this is the particular machine. Here the radiation source is there. What happens is that the radiation source generates IR radiation which comes from here to here, where we have the Michelson interferometer. This Michelson interferometer will help us in splitting the beam and create an interference fringe pattern. This interference fringe pattern will help us in carrying out the experiment, because in this, if you can see from here, this part, here is the zinc selenite crystal, where above it we keep the sample, and this is the sample holder. As you can see from here, we can move it like this, okay, or we can move it like this, depending on how much maximum contact we can generate. And then what we do, we will go for the sample analysis. Okay, so today here we are seeing that this is the screen called the Opus Administrator software. Now here what we do is we try to analyze the spectral scan. So there are different measurements. First we do the measure, set up the measurement basically. As you can see here, as you can see, this is the spectral resolutions are there. So some parameters are set basically. One is called the spectral resolution of 4 cm inverse. Then you have the sample scan of 30 scans and the background scan. So first of all, why we do the background scan basically? We do the background scan here because the background scan is very important in this case. The only thing is, if we don't do the background scan from 4000 to 500 cm inverse wave number, we will not be able to understand how the system works or how the instrument is working. And the spectral resolution is 4 cm inverse, which means that between the two wave numbers, the minimum difference between the two wave numbers is 4 cm inverse. So these are some of the parameters that we use, and the zinc selenite crystal is there. Now first, then we accept and exit, and then we go for measurement, and then we go for the start background measurement. Now why we do this background measurement? The simple funda of this particular thing is that if you don't do the background measurement, we will not be able to calibrate the instrument, because it might be that the instrument might get damaged or the instrument has stray radiations. So in order to cover or order to deter or to remove the stray radiations, we go for this background measurement process. And moreover, if you see the software in general, this software contains a lot of functions. There are a lot of functionalities are there, but in our case, the the point is we have to go for the 30 background scans. So remember that the sample background scan and the background scan and the sample scan must be the same number. The number of the scans between the background and sample must be same. If they are not same, then we will not be able to do a correct analysis. Okay, and then we will initially start with the sample measurement. Okay, so now what we do is we are keeping the sample. This is a chip sample. We are keeping the particular sample piece on top of the ZSA crystal, and as you can see from here, that the sample probe is placed onto the particular sample so that we can have the maximum contact between the sample and the things. Okay, the sample and the crystal must be in the maximum contact. Okay, so now what we do is we will go for the sample measurement. Okay, so now as you can see from here, the sample measurement is going on, and it will start from the 0 scan to 30 scans. Now the most important thing is that in this particular case, it's very important that our background scan is performed before the sample scan. Why? Because if the background scan is not performed before the sample scan, it might be that stray radiations might affect your FTIR spectral sample and we will be doing a wrong analysis. So in this case, what we do, we generally go for the background scan and then the sample scan. Moreover, for FTIR spectral data preparation, in order to prepare for samples, if you want to go for a powder sample, we have to first dehydrate the sample for 2 to 3 hours, and then we will go for this. Now as you can see from here, you are getting the FTIR spectra. So first we will do the baseline correction. Baseline correction means to have a uniform baseline, and then we go for the smoothing. Now we have to remember that smoothing means we have to reduce the number of signals in order to remove the noise. See, now the spectra has come. Now the most important point is that if we are not smoothing it up, we will end up in a wrong analysis. But the smoothing must be done in such a way that your peaks are visible and your peaks is not changed. So the smoothing means you are reducing the number of signals, but at the same time to ensure that your sample nature or signal nature does not change. That is the most important parameter when you are doing the smoothing and then the analysis of the FTIR spectra. And as you can see from here, if you can see the particular thing, this is called the sharp peak. This is again a sharp peak. This is again a narrow peak. So all these peaks are coming by because this is your transmittance. This is your wave number. This one, this is from 1500 to 500 is your FTI fingerprint region, and this particular point from 4000 to 1500 is a functional group region. Now, if you see from here very carefully, why these peaks have come, because there might be that the particular group, functional group like CH group or C double bond group, they have interacted with each other and they have basically done a molecular vibrations, and each wave number corresponds to a particular molecular vibration. Moreover, 1500 to 500, the fingerprint region is the region where each sample has its own characteristics. So it's called the unique spectral signature. Every sample has a unique fingerprint region. Each sample varies with another sample because of this fingerprint region. Okay, and by which we can detect in food technology and other purposes that these peaks are due to what functional groups, what have changed, what have not changed. Hello and welcome. Today here we will discuss in this lecture that how can we analyze and interpret the data, or how to plot the data that we get from the FTIR spectroscopy. First of all, we will get the DPT files. So if you click on this, then we will get this part. Okay, so this is the wave number and this is your transmittance. Okay, remember this. Now we will cancel it. We'll click let's say we'll click a new folder. We'll go to Excel and then we will go for index FTIR data. Okay. Now what we will do, we will simply click on this FTIR data Excel file. So this is a blank Excel file. Now we will simply, what we will do, we will simply go to this DPT file, Control A, Control C, then we will simply paste it here, Control V. So now we will select this column, we will go to data, okay, then we will go for text to columns. Okay. Now in the text to columns we will choose delimited only. Delimited means it will separate the two numbers into two columns. Then next, again we will go for a comma. Comma means it will be separating that. Then general and finish. So here we have got the separation. Now we will simply right click and insert, just to make you aware. This is your wave number in centimeter inverse. Okay, and this is your transmittance. Okay. So this is your values. Now what we need to do is we need to plot the graph. Okay, before we plot the graph, we will go for origin. So we will simply go to the origin 120B as given in the institute. So now we have to plot this data in the origin. So how will we plot? So we will have to paste the data from the Excel file to the origin file in a very important and useful manner. So this window will come, new workbook. Here, so this is your blank workbook. Okay, click on blank workbook. Okay, so our blank workbook will come basically. Okay, so first what we will do, we will select here Control Shift and down arrow. We will copy it and simply will paste it. Again, we will go to transmittance, Control Shift and down arrow. We will copy it and will paste it. I'll also do one thing. I'll also copy another data. Let's say it will be better. Like for example, we can copy this. So we can copy this, Control C. Once your data column is done, you can do one thing. What we'll do, we'll simply paste it. So one DPT is not there. So what we'll do is we'll simply escape it. We'll just copy this value, Control C, and then we will simply, okay, just remove this column, right click, delete, and delete this column also. Okay, so this is the transmittance. Okay, this is the transmittance basically. So what you will do, you can add here, you can add a column. See, so you can add a column here. So this is your, let's say, your wave number. What is centimeter inverse? This is, let's say, S1, S1, and this is, let's say, S2. Clear? Now we can do like this. What we have to do is, in order to get this graph, we will select these three columns, okay, and then we go to line graph. Now if we go to line graph, we can see this is your peaks. I'll show you how to interpret also. So now what we will do, we have to then do the next part. Okay. So this is the way that I showed you how people normally do. But the thing is that there is a catch to it. This is basically wrong. How can we correct the wrong? Basically, to understand the normalize, we have to normalize the data. Normalize means we have to bring the data to a common ratio. Because as it's a transmittance index, so what we have to do is first we will do the max function. This max bracket. We will simply select this, Control Shift down arrow, bracket closed, enter. So this is the maximum value. Okay. So what we need to do is go for insert. Okay. So here we will do equal to this divided by maximal this. Then we'll go for dollar and dollar. Here this is your value. Here similarly again we'll go for max. This one, Control Shift down arrow, enter. So sorry. So this is the max function. So simply what we'll do, we can equal to this one by divided by this one. So simply dollar means the fixing the set. Now we have got the value. Now simply what we need to do, we need to just copy and paste the values in separate file, like separate place for a convenience. These values required. Now this, when you copy and when you paste here, right click values, because otherwise it's a formula. So simply Control Shift down arrow, Control C, then right click values. Here this is the actual data. So first we will find the origin. So now the graph that we will plot now, this is the right graph. Why? Because we have to understand that there are many cases or there are many things in FTIR. Sometimes your spectra might come due to a stray radiation. Sometimes the spectra might come due to any indifference or structural irregularities and many other cases. So we need to understand that how can we plot the right graph in the right manner. So in that case, we will use the normalized data for the plotting purpose. So the same thing, we have opened the origin here. So the same window, blank. Okay. Now, simply what we'll do is we'll simply copy this. Control Shift and right arrow. You're in keyboard, Control Shift and right arrow, then down arrow, copy. You simply paste it here. You paste the values. Now you maximize it. You know that this is your wave number. Okay. And this is your S1. This is your S2. So now we need to simply select it and then we'll paste line graph the same manner. Okay.
Now we need to double click on this axis to change the axis numbers and to make sure that the graph starts from your higher wave number to the lower wave number. Okay, so for that case we need to wait it because sometimes it might be slow because of the system. So we have to look for 4000 to 500. We know the wave number range and the increment is 6. They count by 1. Okay. So it's done. So now we need to go for this. Now it's transmittance index. Clear? This is the wave number, so you can simply bold it. The option is there. If you just select on Control A, Control B, your bold is there. Double click, Control A, Control B, bold is there. You can simply change this by right click and then you can change the font by English italic, Times to Roman for type, then Times to Roman. Okay. Depending on whatever you want to do. This is again Times to Roman. Okay. And you can also bold in this. You can bold. You can also bold this. And how to export the graph? In order to export the graph, you need to go to File. You need to go to Export Graphs. Then Open Dialog. Okay. Now be very careful while exporting the graph means for the pictures, pasting and all. While to show your data in PPT or something like that. So image type normally we go for PNG, but for the best or like format we go for TIFF. TIFF takes a lot of data, like a lot of space. So normally we go for PNG, and then we have to choose that from the in this. So remember this. This is your three dots in which folder will save, and then if you go for the DPI resolution, normally we go for 600. 600 is okay. So the image will be exported in the location. And to close the, we need to close it. Okay. So in this way we can plot the right FTIR graph. Now how will you interpret the data? You can interpret by using this data reader. See, the data reader will simply click on this. If you simply click here, see the wave number is coming. So this is a wave number. This is the intent, the transmittance index. Similarly like this. So this is called a broad peak. If you go for this, and also there is a point called screen read, data cursor. Data cursor, if you go, so what to do is you can maximize it, like you can just maximize the tool, and then you can go for data highlighter or data highlighter. See, S1, then S2. So you can basically see, you can see the change. So this is called a broad peak. Okay, this is called a broad peak. So this is a broad peak. This is a narrow peak. Narrow sharp peak. This peak, the sharp peak. This is a narrow peak. This is a small peak. So you need to understand these peaks very carefully. And remember, the higher the transmittance and the lower the absorbance, the higher will be your peak intensity, the transmittance index. Thank you so much.